Okay, let's begin the lecture. And we continue on the subject of guided waves. And what is a guided wave? Well, as an example geometry, you could look at, for example, a metal. And then glass on top. And then air on top of that again. So it's a thin film of glass, or it could be some plastic or whatever, but let's say glass to have an example material. Then we have a region in the dispersion diagram, omega versus k parallel. So this is the light line for air. So to the left of this we have propagating modes in air, and to the right of this we have evanescent modes in air. And we always have evanescent modes in the metal because it absorbs energy, right? The Ohm's law. This is the light line for the glass, meaning that to the left of this you have propagating modes. To the right of this we have evanescent modes, meaning that in region 1 here there is light that is propagating in glass, but evanescent in air and evanescent in metal. This means that if there is some sort of wave traveling along this interface, it has to be traveling only inside the glass, because outside it's evanescent. So it's kind of stuck in this glass, and we call that a guided wave if it's propagating here in this this part of the dispersion diagram. Yep. And we will find that not all combinations of omega and k parallel will in fact allow you to have guided waves, but we'll find out today how you figure out what parts of this area is actually, well, not for this geometry, but equivalently for another geometry, what combinations of omega and k are allowed to actually have a propagating wave. And we're going to look at the following example. That is a waveguide stretching along the x3 axis, which has a constant cross section. So if I have the x3 axis here, say x, let's see, yeah, that's correct, I hope. And now if I have some cross section like this, in general it could be anything, then it's just a metal pipe stretching along x3, and we assume that the conductor is perfect, that this metal tube of ours is a perfect conductor, meaning that sigma is infinite. That's it. Okay, perfect conductor. And again, this means that our boundary conditions, which we know are very important, at least we know that now, are the following: that E parallel is equal to 0 at the interface. And equivalently, or similarly perhaps, H parallel is equal to 0. This is because there's no electric field in a perfect conductor, right? Because whatever the electric field I insert, the electrons are going to race the other way to get rid of the E field. This is perhaps not quite as obvious, but if you consider the Faraday's law, that dt of B, that's proportional to the curl of E, right? But if E is 0, this has to be 0 as well, meaning that because there's no E field, there can be no B field if I started out with no B field or H field equivalently. Okay? I assume that the metal is not magnetic, so we don't run into any problems there. Okay? So this follows from the Faraday law that if I start out with no B field, the E field can't create one. Okay, and if you think about the geometrical picture which you're used to in reflections and refractions at interfaces, for example, you can think of this as some sort of tube, and then there's a wave bouncing up and down here. So if k is going this direction, at some point in time, it's going to go down again from the reflection at some later point and keep bouncing inside the metal like this because it can't get out. So that's the geometric picture, but it's not correct. It's okay if d is a lot bigger than the wavelength of the light. But if d is on the order of the wavelength of the light, then it's not okay. Because then the wave nature of the electric wave is going to be important, and we need to solve the Maxwell equations with the boundary conditions to get this right. Now to introduce a bit of terminology, if you have a waveguide stretching along, well, the x3 axis, then we say that if there is no electric field along the x3 axis, it's called a transverse electric wave. And that has E3 is equal to 0. That's the definition of transverse electric. And this means that H3 is not equal to 0. You can see this most easily if you look back at the geometric picture. If the E field is perpendicular to this axis, well then, if the H field is like this perhaps, perpendicular to K, well then it's not 0 along the x3 axis anymore, right? Because of the confined space I introduced. So a transverse electric wave has no electric field along the direction of propagation, but it does have an H field. And similarly, we define transverse magnetic. Simply by saying that H3 is equal to 0. In some types of waveguides, we can also have something called transverse electric and magnetic, TEM. And this is, well, it's pretty obvious. It's a wave propagating with no electric or magnetic field along the direction of propagation. So it's transverse, magnetic, and electric. And let's see, in that case we have simply that E3 vanishes and H3 vanishes. Yep. So what we need to do to figure out what happens in one of these waveguides is to solve the Maxwell equations with the boundary conditions listed over there. And I will assume a solution traveling along the x3 axis, which seems pretty obvious that it must be traveling in that direction, and on the following form. So if I say that E is equal to some E naught, R T is equal to E naught of x1, x2 times an exponential like this. So there's some wave traveling in the x3 direction, and there's some electrical field depending on the position in the plane perpendicular to the direction of propagation, which is not trivial anymore. It's not simply a constant like in a plane wave in vacuum, because it has to be 0 at the edges, but then hopefully more than 0 in between, otherwise we have just nothing, which is very little interesting. So if I call this equation 1a, it should be obvious to you by now that I will also have a magnetic field. So I write this as H equal to H naught times the same exponential. Okay, and this suggested solution of mine will have to satisfy the Maxwell equations, or equivalently the wave equation, and the boundary conditions. Okay, the wave equation, you know how that looks. It's simply del square E minus 1 over c square double time derivative of E equal to 0. And it looks exactly the same for the H field. Now if I substitute 1a into the wave equation, I get the following. If I well, when I take the derivatives, I will sometimes get down something from the exponential, but the exponential remains, so I can just take that away, and I get that d1 square E naught, which is now not a constant. It's a function of the position in the plane transverse to the direction of propagation, d2 of the same vector, minus k square E naught. This is from the derivation in the x3 direction, omega square over c square E naught. And this is from the time derivative. I get down an I square, which gives me the sign. Okay? And this is, of course, dependent on x1 and x2, but I don't write it explicitly. And for the H field, you get the same thing, d1 square H naught plus d2 square H naught plus omega square over c square minus k square H naught equals to 0. Like this. And it turns out that in our geometry, where we have simply a hollow waveguide, which is, well, it's just a tube basically, and there can be no transverse electric and magnetic. There can be no TEM waves. And the proof goes as follows. If I set up the Gauss law, it will look like the following. d1 E1 plus d2 E2 is equal to 0. This must be so because it's supposed to be a transverse electric and magnetic wave, so there's no E3, right? And if I set up the Faraday law, I get that d2 E1 minus d1 E2 is also equal to 0. There should be an H3 here, right? But I said that it's going to be transverse electric and magnetic, meaning that H3 is also 0. Which gives us this equation. And now we see that the E field has no curl and it has no divergence. This means that I can write E naught vector in the following way. As the gradient of a potential. And the potential V will have to satisfy the Laplace equation because there's no free charge anywhere. And the Laplace equation has the boundary conditions that on the surfaces it should be 0 or a constant. The potential should be constant on the interfaces, meaning that the simplest solution to think about is just V equal to 0. And this fits the boundary conditions, it fits the equation. And therefore there's no electric field, meaning we cannot have TEM waves. Equivalently, you can show that a solution to the Laplace equation has no local maxima or minima, meaning that you can only have saddle points. And then if the boundary conditions are 0, you can't have anything more than 0 or less than 0 at a minima or maxima, meaning that the potential has to be constant throughout the whole system. So this means that there's no TEM wave. However, for other geometries of waveguides, such as if you have a metal core, like in a coaxial cable, which I'm sure you've all used on the lab, then you can actually have transverse electric and magnetic waves, because then you can have two different constants for the potential on the inner and the outer, say. So this proof breaks down and you can have TEM waves. But let's get back to the waves that can exist in a Holo waveguide. And first of all, we show that the EX, EY, HX, HY, these fields are all functions of E3 and, well, EZ and HZ. And we do that by inserting our suggested solution, E is equal to E naught of x1, x2, e to I k3 minus I omega t, no, let's see, z. Sorry about the mess. E to I k z minus I omega t, just the same as before. We insert these into the following two equations. I get a mu naught because it says B on the right hand side, but I assume that there's nothing inside the waveguide. This is the Faraday equation, and Ampere's equation says this, that the curl of H is equal to the time derivative of the E field, essentially. And if I insert this suggested solution of mine, the ansatz, into these two equations, I get 6 equations if I write it out on component form. So I get 6 equations and 6 unknowns. There are 3 components for each of the E and the H vectors. And if I write down, yeah, let's see. And note that, again, d3 of E, the wave, is equal to simply ik E, and that dt of E is equal to minus I omega E. And if I use this harmonic dependence on time on x3, when I insert this, I get somewhat simpler equations. And if I now write out 2 of these equations on component form, we see that we have ik E1 minus d1 E3 equal to I omega B2. I think I mixed a bit with using XYZ and X1, X2, X3, but I hope it's not, I don't think it's a problem for you. And yeah, the next equation is D2 B3 minus IK B2 is equal to minus I omega over C E1. Okay. If I want the H field again, I will just have to insert a mu naught. Now you see that I can eliminate B2 from this equation, meaning that I only have E3, B3, and E1 left. Meaning that if I eliminate this component of the B field, B2, I will get E1 as a function of B3 and E3 through some derivatives. And then I will get the following. You can do the algebra yourself if you're interested. Okay. Let's see. Okay, keep that stuff for now. Okay, so what we end up with is that E1 is simply a function of B, H3 and E3. So E1 is equal to I omega over C minus K squared K D1 E3 plus omega mu naught d2 h3. Okay, that was a lot of math. Point being now that I assume this formula solution here, and I show that because of this specific formula solution, these derivatives are simple. Then I get out that I only need to find out the third component, the component along the direction of propagation. And from that, I can actually just calculate the other components when I need them. Okay, so I can solve the equation for only H3 or E3, and then I have the full solution. And then normally we work only with transverse electric or transverse magnetic waves, and then if you need something more general, you add them through superposition. But this means that typically if I have a transverse magnetic wave I want to investigate, then I will only get this term. So through one derivative I can get any of the E and H components which are not along the direction of propagation. This simplifies the equation solving. And I won't go through the details because there's 6 of those equations to write up. But you proceed in exactly the same way, and then you find E2, H1, and H3. And they will only depend on E3 and H3 through some derivative. It's done in more detail in the book as well if you want to check this. Now the problem we're going to solve here as an example is the Holo waveguide with a rectangular cross-section. It looks like the following. If I have the x-axis here, y-axis here, we have some size b along the y-axis, a along the x-axis. So a rectangular cross-section, and it stretches out in the x3 direction. So let's see. The x3 axis stretches along the conductor. Okay, so is this picture clear? It's a hollow rectangular pipe, which stretches out to plus minus infinity in our calculations at least. Okay, and now if we look at transverse electric, then we know immediately that transverse electric means Ez is equal to 0. So we need only to solve for H3. And if I let's say H set then. And if I write down the equation for that, it looks like the following: dx square H set plus dy square H set plus omega square over c square minus k square H set. Okay, and now we're going to try to see if this equation is separable, meaning that I will assume a solution for H set on the following form. H set is equal to large X of X, the position in X direction, large Y of Y in the Y direction. Okay, and if I insert this into this equation here, then I will get the following out. Let's see. Then I will get simply, it should be pretty simple. We have y times the double x derivative, which acts only on this. So it's d square x over dx square plus x times d square y dy square. And then there's the omega square over c square minus k square x, let's see, x dot y is equal to 0. And now, same procedure as last year. 1 over x times y. Multiply on both sides, and then I get rid of the x times y here. This one goes away, and this one goes away. So I will get a term here, which depends only on x. I get a term here, which depends only on y. And I get this term, which is constant. This is constant, and if this is going to be true for all x and all y, well, these two better be constant as well. And in general, you need to check all the sign combinations, but I've cheated. So I know that this I can set to minus ky square, and this I can set to minus kx square. Okay. So now we have three equations, and they look like the following. Let's see. Yeah. So one equation for this term here, d square x dx square plus k x square x equal to 0. So it's a simple oscillator equation. Same for y, essentially. Like this. And I have finally what will give me the dispersion relation, and that is kx square minus ky square plus omega square over c square minus k square is equal to 0. So that's equation 3. There we go. Now we just solve these two equations separately, subject to the boundary conditions, and see what we get out. By the way, I think this was a bit unclear. I set, well, since all the terms are constant, I set all the other terms to be kx, right? So this term is constant, but I put it equal to the other constants. That's kx and ky. All right, now solving the equations. And the equation looks like, well, a harmonic oscillator, basically. So I can just write down the general solution of equation 1. And that is that y is equal to a sine of kx x, and then a cosine term, b cosine k y y. And now I need to use the boundary conditions to find out what is b and what is a. And let's see the boundary conditions for that. If I look at the following. Let's see, age x at interface is equal to 0. Right? The parallel component of the age field is equal to 0 at the interface, meaning that age x has to be 0 at the interface. And if I look at what age x is, it is simply I over omega square over c square. minus k squared. Then k dx h z minus omega epsilon dy ez. And in the transverse electric mode, this is simply 0. Right? Meaning that hx is simply the derivative, the normal derivative of hz. X derivative, sorry. Well, yep. So we have that d large X dx at x equal to 0. That's one of the interfaces, right? Is equal to d large X dx at x equal to a. That's the other interface, is equal to 0. So the x derivative of hz, that's just hx. Right? That was clear? Has to be 0 at the interface. And now I find that a has to be 0. Let's see, a is equal to 0. Because, well, at x equal to 0, the derivative of this is non-vanishing, meaning that it doesn't satisfy the boundary condition, so I can just wipe that out. And I get a condition on kx, a quantization condition on kx. Which looks like the following, that kx is equal to m pi divided by a. Because the derivative of the cosine, that's 0 at x equal to 0, so that's fine. But if I want it to be 0 also at the other interface, at x equal to a, then these k's have to be just so that I'm only half a wavelength, or 1 wavelength, or 3/2 of a wavelength, and so on in this oscillation when I get to the other interface. So I make sure that it's always 0 there. Okay? And m, of course, is an integer. B equal to 0? Why do you want B equal to 0? Right, but it's the derivative. So the derivative is a sign which vanishes at 0. Okay? And I have to match the k to get an integer number of half wavelengths to hit the other interface. Okay? And similarly, in the y direction, the equation is exactly the same, meaning that we get ky. It's a cosine solution in that direction as well, but ky is equal to n pi over b, n is equal to 0, 1, 2, and so on. So it's exactly the same math. Okay, and hence hz, this is the prefactor now to the exponential, which depends on x, y. It's simply some constant hc, which is the amplitude, and then cosine kxx, and times cosine kyy. And from equation 3, I get the wave number. And that is as follows. K is equal to omega square over c square minus kx square minus ky square under the square root. So in a vacuum, when there's no confinement, we can have any combination of k and omega as long as they satisfy the dispersion relation. Same thing here basically, except that we got a quantization condition on the transverse dependence on the field. Okay? Because ky and kx can't be just anything. In a vacuum I could choose kx and ky freely and then kz will be given. Here I will have to choose an integer combinations of n and m to satisfy the dispersion relation. I can rewrite this on the following form. Omega square over c square minus pi, then m over a square plus n over b square. And now I call this part omega mn. And yeah, over c squared. Like this. So now, to have a propagating wave, what's the requirement on k and omega? You can discuss for 1 minute, and then we need an answer. Yeah?
K is real if it's a propagating wave?
K should be real, yes. Meaning that if you look at this equation, then this term has to be smaller than this term, right? This means that omega has to be bigger than omega mn. And for this reason we call omega mn the cutoff frequency of mode mn. Because if omega is not larger than this cutoff frequency, we cannot excite this mode anymore. We'll just get evanescent mode. So they might propagate a short distance into the waveguide, say, but they won't really propagate along the waveguide. It will be exponentially damped. Because this k is simply, it's not real anymore. So we get I square, which turns into a minus sign, and the wave turns into an exponential decay. So the idea is basically the same as when we worked on this interface reflection problem. That k has to be real to have a propagating wave. Yeah, so we called omega mn a cutoff frequency. And we need that omega is bigger than this. In order to have a propagating wave. So I can, yeah, let's see. If I plot this now, I will get the following. K and omega in the dispersion diagram. I will have the light line, which is omega is equal to k times c. And but here we see that if k goes to 0, well, this just means that omega mn is equal to omega. So if I have, let's see, omega 1, 0, omega 2, 0, because you see that as I increase the m, they increase, you get something like this, that the dispersion relation starts to approach the light line when this term becomes small compared to this term. But for small case, the difference is important, so you get something that flattens out for small wave numbers. Okay, and from this dispersion relation we can now calculate the phase velocity. Which is simply omega over k, and the group velocity, which is d omega dk. Now you'll immediately notice some funny things, which is, for example, that at small case the group velocity disappears and so on. There's one tricky thing which I want you to think about, and that's the following. It's not so tricky, but it's not very intuitive either. So if I write down V, that's just omega over k, right? The phase velocity. I can write that out explicitly as omega square over c square minus pi. No, let's see. If I solve this equation for omega instead of k, then I will get this relation. I get k square c square plus omega m n square over k. Right? If I just solve this for omega, write it on this form. This is the phase velocity. And if you look carefully now, if I divide by k inside here, I will get that you get c square plus omega m n over k square. And omega mn is positive, so my god, it's greater than the speed of light. And why is this okay? Why is this okay?
Because only the group velocity matters?
Exactly. There's no, for example, there's no energy transport of this at this velocity. And the group velocity you see, at its steepest, it is the same as in vacuum, and then it's actually lower. Okay, so the group velocity is just fine, just that the phase velocity does not look fine. But this is okay. This is how it's supposed to be. And I'm not sure if I have all that much more to say. So, well, just to summarize what we've done on a different example. Let's see. Just to make a different example, which will show what we've discussed today, is the following. If it's an optical fiber, let's say you have a low N here, and then a high N, and then on the outside you have a low N again. Outside the fiber, the x3 axis is just like this. Now, if you want to solve these equations for that we discussed today for the optical fiber, for example, you proceed in exactly the same way. First of all, you write down a suggested solution for the wave equation. And then you impose the boundary conditions, which is at this interface here between the two materials. And then there's another boundary conditions here. And then you need to sort of constrain your solution so you get you will get some quantization condition here as well. In fact, you can even have fibers where the quantization condition is so strict that you can only get a single mode. It's called a single mode fiber. There's only one mode you can excite in the fiber. Similarly to let's say if you have solve a particle in a box in quantum mechanics, if you give it the right parameters, there's only one state the particle can be in. The only real difference between the waveguide in the metallic waveguide for radio waves, which we've been discussing now, and this optical fiber, is that the boundary conditions are now soft. At the metallic interface, we said that E is equal to 0 and H is equal to 0, while here you will have some other boundary condition, which is that the D field, for example, is continuous, as we discussed, showing again that the boundary conditions are really, really important. You need to know them on the exam. And well, that's it. So this just transfers to that problem as well. And I found a phenomenon related to the evanescent field, which I showed on one lecture with the laser light, is that if you have two fibers going parallel to each other, if they get very close and almost touch, then mode from one fiber can in fact tunnel into the other fiber. So you can get loss of light in one fiber going into because there's energy going into a different fiber. This is something that well, fiber engineers have to take care of when they construct optical fibers. And as a homework, I suggest that you go home and read Griffiths on the coaxial transmission line. Griffiths does this for a metal, but the idea should transfer to this case as well, except now the boundary conditions are different. So now you know the physics of that. Any final questions? Okay, see you on Wednesday.